Hello, can you guys hear me? Great. Wow. Welcome, everybody, to my talk on bringing machine learning into your apps with MongoDB. We were actually supposed to have an MC, but we had to send all the MCs home because there's too many people here today, so I'll be MCing myself as well as giving the talk. If anybody has any questions, I'll ask that you hold them to the very end, and I'll be off in the corner. So those that are willing to stave off their lunch, feel free to ask me any questions on any of the content that we get through. We have a packed agenda, so we're going to be talking about a couple things. We're going to start by talking about what it means to bring intelligence into your applications, how to use the data that underlies your application to make machine learning applications sort of drive better customer experiences and more efficient operations. We're gonna demo of an intelligent e-commerce store, and then we're gonna shift gears a little bit, talk about accelerating your AI journey by looking at the different ways that MongoDB can enable machine learning operations. And then finally, we're gonna talk about the buzziest thing. Sahir mentioned this in his keynote, but it's kind of inescapable at this point. We'll be talking about generative AI. And demoing a retrieval augmented generation app using Atlas Vector Search, which is the product that I'm the product manager for. All right, so I think it's probably most important to ground the discussion of machine learning in terms of how it can help your business. We really view machine learning as a means to differentiate your business and become more competitive. The first way you can do this is by building better customer experiences that are backed by AI. So this can take the form of enhancing customer experiences, taking actions on behalf of the customer automatically based on the signals that are present in their usage of the application, and just overall improving customer satisfaction with machine learning-driven experiences. And then the second one is improving business efficiency, so making intelligent recommendations and driving intelligent decision-making using fresher, more accurate data, whether it's through batch machine learning processes or real-time machine learning. There's many different use cases for machine learning across these two segments, improving customer satisfaction, improving business efficiency, across retail, healthcare, finance, and manufacturing. Whatever your application demands, there's probably a machine learning solution that will make it even more competitive. But let's kind of take a step back first. Before we talk about generative AI or even real-time machine learning, it's probably good to review how we got here. Beginning with analytics as a way of generating insights from data. Typically, you would collect metrics on how your users were using your application and use that to drive better business decisions. This is sort of the original way of leveraging data within a transactional database like MongoDB or a relational database. But it does require sort of like the human in the loop component where you can't automatically leverage signals that are present in your data that can be learned via a machine learning model. That's sort of the step 2 here. So using batch AI, you can use the large amounts of data you have to train machine learning models that can make inferences and predictions about future events automatically. I think the main purpose you might want to bring AI into your app is to leverage data in ways that you as a human might not know ahead of time you will need to, and in a way that's much more automatic and generalizable. So we've sort of seen in the past decade all sorts of applications sort of arise out of leveraging data for batch AI. But there starts to become a need for real-time AI when you're dealing with applications that have user interactions that might adjust the inference or the training that you would need to do on a much more frequent basis. A good example would be like an e-commerce store where every user's interaction might drive a different type of prediction, or TikTok or some other content that has micro interactions that will drive a recommendation system on a much more frequent basis, where batch processing isn't as useful as on-the-fly processing. And then finally, generative AI. So sort of the buzziest, most nascent field of AI that's being used to power many applications built on top of MongoDB, generating new content from the data or the interactions that have been provided, typically based on foundational large language models or image generation models. Fun fact, all these images were generated using DALL-E, so there's already generative AI sort of in this presentation. A little gimmicky, but it's good to always remember that it's very much ever present these days. So we're going to look at an example of a fictional e-commerce store where you can buy MongoDB swag that's powered by each of these 4 types of data systems: analytics, batch processing, real-time AI, and generative AI. So in this store, Mongo store, you as a user would sign in. This is a very typical user flow. And based on the user that signed in, you would have personalized recommendations in addition to sort of the general user items. So that's an example of batch AI as a means of enhancing your application. If you were to sign out of this application and sign in as some other user, you would expect to see those personalized recommendations change. So this could be built via collaborative filtering model or content-based model, which is trained offline to improve content recommendations. Now let's say this user wants to purchase equipment and then it goes out of stock, and you would want to update their recommendations accordingly. That would be an example of real-time AI, where you can account for data as other users are interacting with your application to change the recommendations for your user. Finally, you can integrate chat-based experiences over the data that's being searched to incorporate generative AI into your application. So you can, instead of having a very specific search query, ask a chatbot sort of generally the requirements of what you're looking for your camping experience, and the chatbot can provide a set of options that are relevant to your conversation. So yeah. We kind of view like each of these 4 things as requiring their own requirements, as we'll talk about. So the first sort of idea for analytics, the main thing that undergirds all of it is the document model. So your application is based on MongoDB document database, and this enables things like full text search and filtering to do sort of basic analytics over your application data. Moving forward, if you were to do something like build a recommendation system, you might want to use something like Atlas triggers and functions to sort of kick off the inference of a recommendation system model and provide examples back to the application. So that would be an example of batch AI. So the recommendation system model is trained offline, and then inference via triggers allows recommendations to come in to the application. And then for the example of lost cart item updates, you can use Atlas stream processing, as we announced earlier in the keynote, as well as triggers and functions yet again to process data as it comes in off of a Kafka stream or some other stream processing system, like Atlas stream processing, to kind of keep your recommendations fresh as the underlying data changes in real time. And then finally, chatting with your data to generate recommendations. It's kind of missing a thing, but Atlas vector search can be very useful. I built these slides. I should have added that there for sort of undergirding your chatbot experiences with your private data, in this case, with your e-commerce store data. So that kind of gives you an idea of the sort of evolution of AI apps. It might be useful to think now about how does MongoDB Atlas fit into this? What are the components at the data layer, and what are the integrations that make it easier to build these kinds of AI-powered apps? At a high level, AI workflows typically involve 3 parts. There's the data preparation stage, where you get your data from various sources, from your transactional database, from an external set of data stores that maybe are related to the data that's stored in the transactional database, and prepared in typically a cold data lake, which is then used as a feature store for training. Then you have your model training step. So this is a component where you essentially need to store your model or use the data that is stored in Atlas to feed it to your training algorithm, your deep neural network, or XGBoost or some other kind of machine learning model that you're using, most likely, importantly, off of the Atlas platform. We don't provide a training process today, but we provide a number of ways to integrate with other data science platforms where training could occur. And then finally, model inferencing. So this is kind of where you see Atlas coming back into play. So in addition to being a host for feature store, it can be where you store the results of your model inference, which would, again, likely occur in another platform. So in this way, you can easily combine data from MongoDB with non-MongoDB data for data preparation. You can combine Atlas with other data science platforms for model training and inference, and then store the results of those inference within MongoDB for faster retrieval for other services in your application. So what does this look like? So you would typically start with your application. Obviously, you would have an application database, which is MongoDB. And then you would have these external data sources, which would then get federated together with your MongoDB application data in the data preparation step. This would then typically be transformed into a single data lake layer. Well, this is known as like the cold data, which can be stored also in MongoDB. And this data is then used for model training. Models that are trained are typically stored on a model registry, again, with an external ecosystem partner. And then the model that is used at inference time will be pulled from the registry, and the results from that inference will be stored within the application database for faster retrieval from the other services in your application. So I think it's worth sort of taking a step back and saying, like, OK, these are the different components of my AI workflow, but like, how does MongoDB as a data platform fit in? At a high level, there's three sort of like pillars that enable this. So the first is the core database. So MongoDB, you all know it, you all love it. It supports a very flexible document model for as your features evolve and your model requirements evolve, storing various schemas of features and various schemas of inference, of your model inference. We also support ACID transactions and search over your database. In the middle layer, this is sort of the components that enable integration with other machine learning providers. So Atlas Vector Search, put simply, wouldn't work if we didn't have external providers working with it. We don't support embedding within Atlas today. You would have to do your embedding of your unstructured data using some third-party provider. But then that would get stored within Atlas, and we would index your vectors and enable them to be a way to get to your documents most effectively via vector search. Triggers are a way for automatically embedding data that comes into your database. So if you have source data that might be unstructured data, let's say a review for an item in your e-commerce store, you could automatically embed that review using Atlas triggers that was watching that review fields and generate a vector for that data. You can also use Atlas triggers for triggering things like offline or online model training based on new data that comes in. And then finally, Atlas Data Lake for tiering data for that data federation piece. And then the third piece is scale. So being able to auto-scale your clusters as traffic scales up and scales down is a very useful feature of a data platform. Also being able to scale across providers globally. As Sahir mentioned, I think it's 111 different regions that were supported across the public clouds, as well as secure queryable encryption for protecting PII that exists within your feature stores or your transactional database. So all of these things kind of work together in a unified way, but as I mentioned before, most data science, training and inference still will be occurring on an external AI platform. So it's important to understand the capabilities of the data layer and then the sort of integration touch points with ecosystem partners that enable training, inference, model registries, and the like. So I'm not going to go through each and every one in each of these columns, but there's a variety of connectors that enable data preparation within MongoDB Atlas to work with other data sources that are outside of Atlas. For model training, as I mentioned, we support building offline feature stores, as well as being able to quickly and easily create views of features into other data stores. And then model inference, we provide, as I mentioned, an online feature store and Atlas triggers for automatically triggering model inference. There are too many ecosystem partners to mention, but I think when I show you guys the diagram that lays out the high-level AI workflow, I'll also include each of the ecosystem partners, so it'll be easier to map them. But this is sort of a single location to see all the different players within the machine learning ecosystem that we play well with. All right. So to give the quick example of what a reference architecture for personalized recommendations might look like, this is returning back to the original architecture I showed before. And if we look and see what enablers exist within Atlas and what ecosystem providers are out there, you can see that for data preparation, model training, and model inference, there are a variety of solutions to sort of enable these types of workflows. The same is true for real-time AI. So the model architecture looks slightly different. So you're still going to have an application, but typically the data will be streamed to a message queue broker system, kind of like Kafka or Atlas Stream Processing, which then gets sent, the data gets sent to the application database from the message queue. And similarly to before, that data can be federated with other third-party data sources that are used for model training into a cold data lake. And then you can also stream the features from the message queue directly to the model inference step. So as you're getting new data into your system, you can automatically inference that data from data coming from the message queue rather than from the transactional database. And then finally, you can provide real-time predictions based on that data coming in real time. Sort of out of order, but yeah, the model training step still comes from the cold data lake, and the model registry is sort of the layer at which models get pushed from the model training step and then referenced at model inference time. So a simple reference architecture for what this might look like would be a predictive vehicle maintenance application. This is actually similar to the example that Sahir provided, but not exactly the same. So in this case, we want users to be able to know when to bring their car into the shop. So essentially, you have a set of data that the user provides to the application that says, I'm getting this weird sound in my car, or it's been 30,000 miles driven that I'm automatically recording. This various sets of data might be useful to predict, hey, you should probably bring your car into the shop. What might this look like? So you would typically have edge data recorded from the car via the Realm SDK, which can then be federated into MongoDB Atlas. You might have a web platform and a mobile platform that the user can interact with, which again would go to MongoDB Atlas. And then this data can be stored within AWS, one of our supported partners, cloud partners, and used as a means to train models and use them from inference using Sagemaker. So there's a variety of other AWS features that enable direct integration between MongoDB and Sagemaker. But sort of shown here, you can integrate your ecosystem partner, in this case AWS, with MongoDB Atlas for batch ML inference. Moving a little forward from MLOps towards generative AI, again, this is sort of the use case that has, I would say generative AI is actually bigger than a use case. It's the sort of movement within machine learning that has driven a lot of attention and excitement, specifically towards making applications more intelligent by generating content rather than just classifying. Typically machine learning models would be used to cluster or classify data. This is fraud, this is not fraud. But generative AI is sort of a new regime where you can produce new content based on data received. And even further, you can prompt these models with context to allow them to better answer questions without needing to fine-tune. This is sort of a huge unlock for database providers in particular, because we may not be the most expert at training models and fine-tuning models, but if we can enable developers to use these large language models via intelligent prompting and sort of show them the tools on how to do this, then more people can get the benefit of generative AI than previously with previous generations of machine learning, where you really needed a dedicated data science team for something like this. Sort of the canonical example for generative AI is ChatGPT. It sort of kicked off the whole wave. A lot of people like to use ChatGPT for getting advice, doing research, getting recommendations on how to perform a task in a more sort of general way than you might be able to get from a search engine. So large language models are sort of undergirding ChatGPT and other image generation models like DALL-E. They're trained on a massive corpus of data, which means that they're broadly pretty general purpose, but they might have a few limitations. They might be limited in terms of the data at which they were trained, in terms of the knowledge that they have, and they also might be just highly confident about the answers that they're providing, even if there's no basis in reality. Right? It's really helpful to have a general model, but if it gives you answers that aren't accurate or that aren't based on your data, it's not that practical. It becomes kind of like a toy. And so one thing that really helps, or actually, I can show a quick example of what this limitation might look like. So in this case, we're asking ChatGPT using GPT 3.5, how does GPT-4 compare when dealing with hallucinations? And GPT 3.5 doesn't know what GPT-4 is because it was finished training in September 2021, which is well before GPT-4 was ready. So the key here is figuring out a way to use your private data to sort of steer the direction in which the conversation that this chatbot can have goes. Ground it in the truth of your data, but also limit sort of the range of answers it can provide. If you're creating a chatbot that's based on the MongoDB documentation, you probably don't want to be talking about like current events. Like it's a little bit irrelevant to the task, and you can say like, hey, I'm just a chatbot about documentation. Don't really know that much about Joe Biden. So as I mentioned previously, when you dealt with large models and you wanted to have them work specifically for your data, you would do something called fine-tuning. This is still a thing you can do with these foundational models, where you provide a set of examples from your own data and some positive labels that might be used during your fine-tuning process to change the weights of the model. So OpenAI, for example, provides a fine-tuning API where you can do this. Other open source LLMs also have different ways of doing this. But this might seem like a little bit like intimidating for some people. Depending on where you are in your machine learning journey, like having to stand up a fine-tuning service might seem a little bit beyond what you want to do. It might be a little bit too complex. So another approach that people have used is in-context learning, also known as few-shot learning, few-shot prompting, or I guess more recently, retrieval augmented generation, where you essentially, you get a user query, you vectorize it, and you compare it to a database of vectorized documents. So chunks of PDFs of research papers or documentation that are vectorized. That can be, you can take your vectorized query and compare it directly to those chunks, retrieve the most relevant piece of context, and prefix the query that then goes to the LLM with that relevant context. So what does that look like? If you were to build a chatbot securely over private data, what are the different pieces that you need? So broadly speaking, there's four pieces that you would need. So you would need your private knowledge stores. You would need to know, okay, what pieces of knowledge do I want my chatbot to be aware of? You would need to have identified which large language model you're interfacing with. Could be closed source model, could be open source model. You would need to identify what orchestration framework you're using to interface with these different systems. We are supported, Atlas Vector Search is supported with Llama Index and LangChain. You can also just use Python. I think actually today we're also supported in Microsoft Semantic Kernel. And then finally, how are you actually storing not just your vectors, but your documents? Like, are you going to be storing your vectors in one system and searching them and then getting a set of document IDs that are related to those vectors and then sending that to your database and pulling out the relevant collections, or are you going to have them all in one place? We believe it's simpler if it's all in one place. You search by vector, but you get back a set of documents, and those documents contain the information you're most interested in. So at a high level, you would ingest your data using various connectors. These integration frameworks specify ways to parse PDFs or other types of unstructured data and then take those chunks and embed them using an embedding model of your choice. You can then send those chunks and those embeddings to your system of record, your document database, and build a vector search index in MongoDB to enable easy, accurate semantic search. And then finally, your embedding generation and your prompt, your LLM prompt or chat completion API endpoints will then enable you to actually interface with these large language models. To be clear, MongoDB does not build a large language model. We allow people to integrate with our platform, our vector search platform, to interface with these systems with more accurate prompts. Prompts that are weighed in with the context of your private data, I should say. And then finally, the user, all they see is essentially a chatbot interface. So they send in their queries. That query gets routed in the system I showed before, then gets augmented with relevant context that the vector search system yielded. And the response they get is much richer and sort of contains the context of the private data that you have. There's various ways of sort of approaching chunking data for this process. So actually, in my experience as the PM, I often find that this is the stumbling block that a lot of people land on, is finding the right strategy for chunking your data, the right level of context to provide based on the application that you have, finding ways to relate this table on page 3 with this section on page 2 that's related to that table. So often it goes further than just providing 120 characters as my chunk size. Sometimes you need to be able to relate documents to each other. In the case of a table and a section paragraph, you might want to specify parent-child relationships. Very easy to do in MongoDB to define these sort of graph-like relationships in addition to being able to do vector search over relevant context chunks. And then, yeah, I think it's probably worth pointing out, vector embeddings themselves are numeric representations. In MongoDB, it's double precision floating point numbers that represent essentially unstructured data. So sentences, images, audio are represented mathematically with floating point numbers. These numbers contain some idea of semantic meaning for each of these pieces of content that is based on the training process of the embedding model itself. Typically, these embedding models are produced solving some kind of natural language processing task or image captioning task that can then have an intermediate representation of the unstructured data as an intermediate output, which is then usable for things like similarity search. So in the case of a sentence, you would have a text embedding model which would produce a vector of floating point numbers. For images, you would typically use a video or image model. And then audio, similarly, there's audio models. I will say the richest sort of ecosystem around this has been for text models. There's definitely more open source text embedding models than there are for these other two modalities. But I suspect that this will change. This whole field is moving very quickly. And as sort of more use cases become prevalent, I'm sure we'll see more open source and closed source video and audio embedding models. I think it's definitely worth pointing out if you might want to change the paradigm a little bit. So instead of chunking and embedding all your data initially, you might expect your source data to come in and need to be embedded automatically. That much more aligns with the MongoDB model of transactional database, where you have data that is constantly updating, and you might need to have a way of automatically embedding it. So we think Atlas triggers is a great way for automating HTTP calls to embedding model endpoints. Could be open source embedding models hosted on a HuggingFace endpoint. Could be OpenAI, Dataiku embedding model. You essentially define with an Atlas a trigger and a function that would get executed. Given a specific field updating, this trigger would occur, and then you would make an embedding model call that would populate a new field within your document that would be like the embedded representation of that initial field. So we see this as like the current automation within our platform for doing this, but depending on feedback, we might work on making this even more tightly integrated in the future. So, oh. Oh no. What does it say? You need permission to view this video. Oh, that's too bad. Well, I can share that out later, but I had a quick demo on retrieval augmented generation using Atlas vector search. But yeah, I have a couple other resources here for documentation on KNN beta. Within the $search stage, we're also announcing $vector search as its own aggregation stage, as well as the demo that was in video form, and how to use Atlas vector search with unstructured I/O for more complicated ingestion of unstructured data, and sort of defining those graph relationships, as I mentioned before. Great, thank you. So I'm going to be answering questions right over there if anybody wants to ask me questions.